Okay, anybody have any questions about the homework that I assigned? Remember, it was just a couple of problems about just kind of questions about making sense out of how energy changes when forces are applied. No one has any questions about that? Okay, so yes.
From like the last homework slide,
Oh, yeah.
the conservation law.
Yeah.
In terms of like inelastic, what exactly does that tell us about the after collision?
Inelastic means that they stick together. So elastic means that they bounce apart. Inelastic means they stick together. And so when you have an inelastic collision, it means that their velocities are going to be the same after the collision. So instead of having to calculate two velocities, you only have to calculate one. And that's why it's solvable that way. You also, if you know certain things about how elastic it is, it's possible to calculate the velocities of both of the things after the collisions. It's just a little more mathematically involved, and so we're skipping it because, to me, you get the same understanding of the idea without so much just algebra, you know.
Okay, so basically they just like connect together.
They connect together, yes, exactly. Or stick together if you think of it as like Play-Doh or something, yeah. Or a person catching something is inelastic. Yep. So last time we started talking about conservation of mechanical energy. And you can use this idea anytime there aren't big changes in like thermal energy, like if temperatures aren't changing drastically over the problem that you're doing, or electrical energy or magnetic energy, you can use this approach. And I defined two things. Kinetic energy. I said was, I called it uppercase T. And that's equal to 1/2 times the object's mass times its speed squared. So as an object's speed increases, it gains energy. Okay, so think of speed as a type of energy. If an object's slowing down, it's losing energy. If it's speeding up, it's gaining energy. And I defined work as a change in energy due to an applied force. Okay, so how does this work? Well, if you apply a force to something, it can change the speed. We've seen that a lot, you know. It doesn't have to change the speed. Sometimes the speed stays constant when you apply certain forces. But a force can change the speed. And so when it increases the speed, it's increasing the energy of the object. And when it decreases the speed, it's decreasing the energy in the object. So, like, for example, if you think of an object that's moving in this direction, and you apply a force this way, is that going to increase the speed of the object or decrease the speed of the object, or neither? It's going to increase because these are within 90 degrees of each other. Okay. So this is increasing the speed, and therefore it's increasing the kinetic energy. Okay. What about if the object's moving this direction and you apply a force this way? Is that going to increase or decrease the speed of the object? It's going to decrease it, yep, because those are more than 90 degrees. So this is decreasing the speed. And therefore it's decreasing the kinetic energy. Okay, now what if you have an object moving this direction and you're applying a force this direction? So those are 90 degrees from each other. Is that going to increase or decrease the speed, or neither?
Neither.
Neither. All this is going to do, so this is going to cause no speed change. All it's going to do is make this object turn. So this doesn't change the kinetic energy. Okay, so that's pretty easy to understand overall. You know, it goes along with your understanding of things, how to slow objects down, speed objects up. The problem comes sometimes when you're trying to calculate how much the energy increases. So the difficulty can come from calculating how much energy is changed by a force. One thing we talked about last time is there is a time that you can do this. If the force is constant, so if you have the same force vector acting on the object the whole time it moves through a displacement, so as the object undergoes a displacement lowercase d, then you can calculate the work. Okay, the work is equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement. Okay, but that's asking a lot for that force to stay constant as this thing moves. You know, most of the time, what? Yeah. So most of the time, forces change as time goes by. And then what do? You know, then you can't use that equation for work. Okay? And that's why we have to talk about the last thing here, or the last pair of things. We can always calculate the work, though, for what are called conservative forces. Okay, so now we have to define conservative forces. And the definition of a conservative force is if knowing an object's location is enough to know the force, the force is conservative. Okay. For us, there are only two of these conservative forces we have to worry about. And those are gravity, weight, and forces from springs. Okay, so let me try to point out how these work. So let's say we have something and we know the mass of it, like this calculator. Okay, and as I move it around, okay, if I tell you at every instant what its position is, okay, is that enough for you to know the force that gravity applies to it? Well, it turns out that that's even more information than we need the way we've been thinking about gravity, because we think of gravity as just the mass times 9.81 pointing down, right? So if I tell you the position is here, then you say, yeah, that's enough for me to know the force. It's more than I need, in fact. The force is down at 9.81 times the mass. And if I tell you it's here, same thing, no matter where I put it. So this is actually kind of like an extra conservative force. We don't even need that information, but it meets that criterion. You could patiently wait for me to tell you the location, and then you could say what the force is on it, without listening. What about a spring force? How does that work? Well, let's say we attach a spring to the wall, okay? And I attach it to the calculator and I stretch it back here, okay? And we took a measurement of it. Kind of the question is, would it be the same force that it applied to this, no matter how I got to this location? Is information about how far I've pulled it back enough to specify what the force is going to be? So like if I took that force and did this, moved it a couple times and then moved it here, and then separately I took it, stretched it to here, and then moved it to here. The fact that it's at the same location means that that force is going to be the same in both instances. So it doesn't matter like what the path was that I took to get there. The location tells me what that force is. Okay? Let's think about one that's not conservative. So now let's think of two that aren't conservative. So first of all, what about the normal force that the table is applying to the calculator? Well, at first you might think, well, yeah, it's just counteracting the weight. So maybe that's conservative. But look, like now it's in the same location as I push down on it, and I'm making that normal force go up as I do this. So the fact that it's in that location is not enough to know what that force is. Okay, so the normal force is not conservative. What about friction? Is it being in this location enough to know what the friction force is? No, if it's sliding this way, that's a lot of friction. If it's sliding, it does things on both sides, using a staple. If it's sliding this way, when it gets to this location, the friction force is that way, right? If I get to that location sliding this way, the friction force is this way. So it's definitely not the same even though it's at the same location. So conservative forces it's not like a given that something's a conservative force. Just some are and some aren't. But in the case where we have conservative forces, it's really easy to work out that difficulty in calculating the work. Okay. So what is it that makes it easier to calculate the work? For conservative forces, you can determine a potential energy function and I'm going to call that, what did I call it before? U, I think, yeah. Capital U. That only depends on the location. Where, and this is the key thing, the work is equal to the negative change in the potential energy. Okay. So for example, if a conservative force has a potential energy of let's say 50 joules at the start of its motion, and a potential energy of 230 joules at the end of the motion, then no matter what the object did in between, the work done by that force is equal to negative 230 minus 50, or negative 180 joules. This should say a conservative force.
Why is it negative?
Because of this definition of work and change in. Oh. Yep. So there's a negative there. So but based on that, if we know that the work over that motion is a negative 180 joules, does that mean that energy was added or removed from the object by this force? Do you remember that? Removed, yep. And so thinking about it physically, that means that the object was slowed down by that force. Okay? And the weird thing is we don't even have to know whether this took place over an hour or a minute or a second. And we don't need to know if the object went all the way from here to Iowa and back, or whether it just went from here to there. None of that matters. All that matters for conservative forces is the potential energy at the start of the motion and the potential energy at the end of the motion. So you can see how that's a pretty simple way to do this calculation without having to worry about all this stuff going on in between. And maybe you can also kind of have an idea of like how the definition of conservative force lets us do this simple calculation, because if the conservative force only depends on the location of the object, it doesn't depend on the path the object takes, then maybe all you care about are what's happening at the beginning and the end, and you don't care about the in-between stuff. Okay, so that's all stuff, I mean, just kind of understanding what work and potential energy and stuff are. The bottom line is we're going to use potential energy as a way to calculate work when we have these conservative forces. So here are the two potential energy functions that we're going to use. The first one is gravitational. And the gravitational potential energy function is the object's mass times positive 9.81 meters per second squared times the height of the object.
In meters?
Yeah, this is all in would all be in SI units. And so, yes?
Make sure we're considering G not to be negative.
Correct. Yeah, whenever I write that lowercase g, that's positive 9.81 meters per second squared. Anytime the negative is there, that's just a direction that you're adding to it for a vector. And so what this says is the potential energy goes up as an object gets higher. Okay. And then the other one is for a spring. Oh, one thing I want to say about this, like height compared to what, you know? Like, what is absolute height? You know, is it the height from the floor, or the height from the center of the earth, or the height from the sun, or the height from the center of the solar system, center of the, galaxy? You know what I mean? Like, that could be a real problem. The fact is, all we care about are changes in potential energy, and so your height 0, you can just choose whatever's convenient as long as you use it for the whole problem. Okay, so like if I wanted to calculate the height of this for potential energy, I could call the desk height equals 0 and say this is half a meter and this is 1 meter or whatever. Okay. So you can always choose your height equals 0 for any problem. The second one of these is for spring forces. And the potential energy is 1/2 times K times X squared, where this K is the spring stiffness. So if you have a spring that's really hard to stretch, this K value is high. If you have a spring that's really easy to stretch, that K value is low. And X is the distance the spring is deformed from its resting length.
We're gonna do like compression and we're gonna do ones like stretch and compress.
Yeah. And that's an important question. I mean, it's an important thing to consider because, like, does one mean positive and one mean negative? You can think of, so the fact that there's that square there means that the signs don't matter. And so that's kind of the important answer to this is, yes, that's something to consider, but the square takes care of it. So whether that's compressed an inch past, from its resting length or stretched an inch past, that X is just 1 inch. Okay, so here are the two functions we're going to use. Okay, so we've done a problem like this before. So let's say that an object goes from a height. I'm going to use the same numbers I did before. I think these are the numbers I used before. So say an object goes from a height of 5 meters to a height of 2 meters. What's the work done by gravity? Last time we did this, we were able to do it because gravity is a constant force. And so we used this definition of work that I gave you again here. Okay? But now we're going to do it using potential energy. So the change in potential energy is the later potential energy, which is, let's give this a mass too. Did I give it a mass last time? Here we go. 3 kilogram. Okay, so I'm going to use that again. So let's say it's a 3 kilogram object. Okay. So the later potential energy is 3 times 9.81 times a height of 2. The earlier potential energy is 3 times 9.81 times a height of 5. And so we get negative 88.29 joules. Okay. So what's the work? Well, remember the work is negative change in potential energy. And so the work is positive 88.29 joules. Does it make sense that the work would be positive here as something moves down, that gravity would be trying to speed it up rather than trying to slow it down? Yeah, because the gravitational force and the direction the thing is moving are in the same direction. And that's the same answer we got last time. Okay, let's do one with a spring. So let's say we have a mass that can roll. Let's say it has, well, it doesn't even matter what its mass is. I'll leave that off. And it's attached to the wall by a spring. And let's say that this spring constant is given, let's say it's 250 newtons per meter are the units there. What's the work of the spring as an object starts at rest, starts, at the spring's resting length, and then the spring is stretched, let's say 10 centimeters, so 0.10 meters. Okay, so it starts with the spring at its resting length, and then we stretch it. Okay, well, as you pull this thing away from, as you pull this spring away from its resting length, that spring force is trying to pull it in the opposite direction, right? The spring is always trying to get itself back to its resting length. If you can picture what a spring does, if you try to compress it, it'll push to try to get back. If you try to stretch it, it'll pull to try to get it back. And so we expect the force of the spring to fight against this motion. Okay, and so we expect the spring to have a net effect of reducing the energy of this object. Okay, so thinking about it that way, we expect the work to be negative. All right, so let's do this calculation. So the potential energy is the 1/2 times the spring stiffness times the later location, which is 0.1 squared, and then minus 1/2 times the spring stiffness times the deformation at the earlier location, which is 0. This is a change in potential energy. And so we get 125 times 0.1 squared, 1.25 joules. So the change in potential energy is positive. That means that the work, which is negative change in potential energy, is negative 1.25 joules. And so it happened the way we thought. The spring is fighting against that motion and removing energy from the object. Okay, so now based on all this stuff, we can do conservation of mechanical energy. And so think of an object's total mechanical energy at an instant as its kinetic energy at that instant plus its potential energy at that instant. Okay, so that's going to be like our definition of mechanical energy. And conservation of mechanical energy says if only conservative forces do work on an object, then the kinetic energy plus the potential energy at instant 1, any instant 1, has to be the same as the kinetic plus the potential energy at instant 2. So that's it. Okay, so let's let's see one example. If an object falls to the floor from a height of 5 meters, how fast is it going just before it hits the ground? I said that one of the ways you can identify when to use conservation of mechanical energy is when you're relating a location to a speed. And so this has that. But notice this is a problem we also could, we have another way to do a problem like this. This is just a one-dimensional free fall problem too. But let's do this one. Most problems you'll either have to do one way or have to do another way. This one you could do two ways and you'd get the same answer. But let's do this one with conservation of mechanical energy. Okay, so I'm going to set up, this is how I'm always going to do it. I'm going to kind of break it up into a little table. Our instant 1 is going to be when it's dropped. And our instant 2 is going to be right before it hits the floor. What forces are acting on this object as it falls?
Gravity.
Only gravity. And that's a conservative force, so we know we can use conservation of mechanical energy. So we'll calculate the gravitational potential energy before it falls. We don't know what the mass is, so I'm just going to call that m. We're going to see that cancels out, meaning that the speed is the same no matter what the mass is. And we know that from thinking about free fall. Okay, so that's m times 9.81 times a height of 5 meters. I'm going to call my 0 the floor. And so this gravitational potential energy is 49.05 times m. And the kinetic energy at the instant that it's dropped is 1/2 times the mass times the speed squared. What's its speed at the instant it's dropped? 0, yep. And so this kinetic energy at the start is equal to 0. And then at instant 2, the gravitational potential energy is m times 9.81 times the new height. What's the height at instant 2? 0. So the gravitational potential energy is 0 at that second instant. And we're trying to calculate the speed before it hits the ground, so we don't know what that is. So I'll just leave it as v for now, and we'll be able to calculate that. Okay? And so what conservation of mechanical energy says is add up the two things on the left. Those have to be equal to the sum of the two things on the right. So 49.05 m plus 0 is equal to 0 plus 1/2 m v squared. And so that says 49.05 m is equal to 1/2 m v squared. Now both sides are multiplied by m, so I can divide both sides by m and get rid of that. That's how you know that the mass doesn't matter. And so we get that v squared is equal to 98.1. And so v is equal to 9.90 meters per second. And it's a speed, so we want the positive. And that's the exact same answer you would have get, even though those equations don't look anything like it. Those are the exact answers you would get from using the free fall equations, the constant acceleration equations. Okay, well, we did it for this one case where the only force is gravity. Notice that I said that in order to use this, the only forces that do work have to be conservative. So now you have to start thinking, like, how many cases are there that we care about where the only forces that do work are conservative? I mean, there's this one. You could, I guess, do one with a thing hanging from a spring. Then it has a spring conservative force and a weight conservative force. And that's everything, you know? And you could do one in outer space where there's only the spring and no gravity. But basically, not much useful seems like it's going to be able to come from this. Unless some forces that are not conservative do zero work, okay? And so remember, when we talked about work, there is a way that there can be forces, but they don't do any work. And that's if they're perpendicular to the velocity, okay? So let's say our allowable problems are exhausted pretty fast, pretty quickly. Unless forces that aren't conservative often do zero work. Well, it turns out that there are two really important types of forces that have come up in a lot of our problems and are going to keep coming up that are non-conservative, but they do zero work. So, you know, luckily, here are two important forces, important non-conservative forces that do zero work. The first one is normal forces in rolling and sliding. I mean, we've used those kind of forces over and over and over again. And if you think about what they do, like if you have an object that's rolling along a surface like this, the velocity is this way or the other way, the opposite of that. And the normal force is perpendicular to it like this. And so these two forces are perpendicular, always. Or these two vectors, I mean. Okay, so what that says is, okay, now we can, besides just problems that have gravity and springs, we can always include problems that are rolling or sliding you know, the normal force in there doesn't mess up our ability to do this problem. Okay. And then the other important one is centripetal forces in circular motion. So why is that? Well, if something is moving along a circular path like this, its velocity is tangent to the circular path. So any force that's pointing toward the center is perpendicular to that one. And so it does zero work. So what that means is the problems that we're going to do are all going to be combinations of gravity, springs, rolling along surfaces, or circular paths with centripetal forces, like which could be a normal force, or it could be a string or a cable holding it to the center of the rotation. Okay. All right, so let's just do a couple of example problems. This is a funny topic because there's like so much understanding behind such simple calculations, you know. But I think it is really useful to try to wrap your head around all these different terms and stuff. So I am going to put this kind of stuff in quizzes when we have quizzes. And we do have a quiz this week, by the way, on Wednesday. I'll get that on D2L. But okay, so let's say that so we've done problems with setups like this pretty often, where something's swinging around in a circular path, and gravity is acting toward the bottom of the page. Okay. So let's say that this length is 0.1 meters. And let's say first, what's the slowest the ball can be moving at the top of the circle? So it stays in the circular path. And then second, how fast then, you know, if it's moving that speed at the top, how fast is it moving at the bottom? Okay, we did a problem like this before, and somebody asked me, I went to the board, I think, and like did a quick calculation to see how fast it would be going at the bottom. And somebody asked how I did that. We're going to do that with conservation of mechanical energy right now. Okay. And so first we're going to figure out, just using Newton's laws, what's the slowest it can be moving at the top. Okay, so this is just using a circular motion approach. Is this a tetherball problem? No, because it's not parallel to the ground. So I'm going to take a view where I can see the circular path. I was so close to getting a good circle there. Okay. The velocity is this way. At the top and bottom, the height isn't changing. So all we have is centripetal acceleration. The magnitude of the centripetal acceleration is v squared over r. So v squared over 0.1. 1 over 0.1 is 10. So to simplify it, I'm just going to write this as 10 v squared. We can see that that's in the negative y direction. So our total centripetal acceleration is 0, negative 10 v squared. And since there's no tangential, this is also equal to our total acceleration. And now I'll draw a free body diagram. We have a weight force of mg. And we have a cable force down of t. And if you remember the reasoning we used when we did a problem like this before, I think it was a loop-de-loop that we did before, but we said, okay, we're going to assume that it's following this circular path, and then we're going to find when that cable tension, when it can still satisfy that circular path with that cable tension equal to 0. That's the cutoff point between what's possible and what's not possible. So this says 0t, negative t, plus 0, negative, I'll write this as 9.81 m, is equal to the mass times the acceleration and we're going to assume that this t is equal to 0. That's going to be our cutoff point. So then the y equation says negative 9.81 m is equal to negative 10 m v squared. Divide both sides by m. And you get that v squared is equal to, I can do that, 0.981. And so v is equal to plus or minus 0.990. And we want the positive, it's a speed. Okay, I went through that pretty fast, but that was just circular motion. That was just to figure out, okay, if this thing's going to stay in a circle, this is the speed at the top. So now we're going to figure out what's the slowest possible speed at the bottom, because this is as slow as it can be at the top. And we're going to use conservation of mechanical energy to figure out the speed at the bottom. What do you want to use as our height equals 0? The two reasonable choices would be either the center of the circle or the lowest point. I guess I'll choose h equals 0 to be the lowest point. So in order to use conservation of energy, we have to think, are all the forces that do work conservative? Well, there's two forces acting at any instant. There's the weight force from gravity, and then there's that string force. The string force is non-conservative, but it always points towards the center of the circle. Okay, and so we can use conservation of energy even though there's that non-conservative force. Okay, so you can think like, if we think of a free body diagram, hold on. So free body diagram at just some random point around the circle. We have a weight force, and we have a cable force. This one is conservative, so that's fine. This one is non-conservative, but it does no work. So that one's fine too. Okay, so I'll write out a table. Our instant 1 is going to be at the top of the circle. Our instant 2 is going to be at the bottom of the circle. If h equals 0 is the bottom of the circle, what's the height at the top of the circle? Well, the length of the string is 0.1 meters. That's the radius. So the height is going to be 0.2. So this is 1.962 m for the gravitational potential energy. Okay. And then the kinetic energy at that first instant at the top, that's 1/2 times the mass times the speed squared. Our speed is 0.990. And so that is 0.4905 m. With me on that on instant 1. And now at instant 2, what's the height? Yep. That's what we chose as our 0 height. So there's no gravitational potential energy. And then the kinetic energy, well, we're trying to calculate that V, so I'll just leave it as V. And so now conservation of mechanical energy says 1.962 m plus 0.4905 m is equal to 0 plus 1/2 m v squared. Everything is multiplied by an m, so we can divide both sides by m. And we get 1.962 plus 0.4905 is equal to 1/2 v squared. So v squared is equal to 4.905. And so V is equal to plus or minus 2.21 meters per second. And none of the other stuff that we've talked about in this class would give us a way to calculate that. Okay, so if you saw this cold, you know, and had to come up with a way to approach it, how would you recognize that you wanted to use conservation of mechanical energy for this second part anyways? Two things. There's a relationship between a location and a speed that we're dealing with. So that's a good sign. And then the second thing is when you look at that free body diagram, you see that the only forces are in that category of 4 forces that are possible for this. Gravity, springs, normal force in rolling or sliding, or forces toward or away from the center of a circular motion. Okay, let's do another one that's a little simpler. And as simple as this is to do, we don't have another way to do a problem like this either. So let's say there's a skier, starts at the bottom of this the top of this hill. Let's say the height of the hill is, what did I say before? Let's say this is 10 meters high. That's not much of a ski hill. And let's say if the skier starts at rest, how fast will the skier be going at the bottom of the hill? Well, first we have to think about, so how would we know that we wanted to do this with conservation of mechanical energy? One thing about it is it doesn't give any details on the path. And so that also can be a giveaway for conservation of mechanical energy. Like we don't know, I gave this crazy shape of this hill, but I didn't say anything about like any mathematical description of it. Also, we're trying to relate a location to a speed. And then third, the forces on the skier at any instant are a gravitational force and a normal force in sliding. So those fit into the category of things that we can deal with. Okay. All right, so instant 1 is going to be at the top of the hill. Instant 2 is at the bottom of the hill. I'll choose h equals 0 at the bottom of the hill. The gravitational potential energy at the top of the hill is the mass times 9.81 times a height of 10. So that's 98.1 m. The kinetic energy at the top is 1/2 times the mass times the speed squared, and the speed is 0. So this just comes out to be 0. Anything that's at rest has a kinetic energy of 0. Then at instant 2 at the bottom of the hill, our gravitational potential energy is m times 9.81 times a height of 0. So this is just equal to 0. And the kinetic energy, we don't know what that speed is, so I'll just write it as 1/2 times m times v squared. Now put these in the equation. You have 98.1 m plus 0 is equal to 0 plus 1/2 m v squared. You can divide both sides by m, and you get that v squared is equal to 196.2. So v is equal to 14.01 meters per second. The amazing thing about this is, so this hill is 10 meters high, which is not a very high hill, 30 feet or something. That's a really high speed for someone to be going on skis. That's, let's say, 30 miles an hour, okay? And so if you start on a ski hill at 10 meters high and ski straight down, you won't be going 30 miles an hour. So what's the deal? The deal is friction. There's just a lot more friction than you think there is when you're skiing, And when you do all the turns and stuff, you're just doing that to try to get more friction. So, but if there was no friction, this is how fast you would be going. Any questions about that? Okay. So we've only done gravitational problems so far. I'll give you a couple of those to work on. And on Wednesday, we'll do some spring problems. Also, we didn't have lab last week. We don't have lab this week. And we won't have lab next week for Thanksgiving. So we're on this long break of labs. I will be in the lab room for anybody who wants to come ask questions or go through problems or whatever. So feel free to think of that as like extra office hours or study hall or whatever. But I'm not taking attendance or anything. Okay, that's all.